So in this part of the course, we're going to look at how we can use different techniques to make implementations of coherent shared memory more scalable. There are at the high level, there are three different options how you implement scalable shared memory. We have the kind of systems we've been looking at so far, which are the uniform memory architectures, or sometimes also called symmetric multiprocessor, so UMA or SMP. The property of such system is that the access time from any processor to any part of the memory is uniform. So it doesn't matter where you place a thread to execute and or where you place some specific piece of data in the memory, because it's all uniform. So that's what you, for example, get if you have the Snoopy-based cache coherence protocol that we looked at before. But you can also implement these kind of architectures using a non-snooping kind of coherence, and we can discuss that with directory-based implementations in the next lecture. But there are more scalable ways of implementing shared memory as well. So there is something called non-uniform memory architectures, or NUMA for short, where this property of uniformity between memory and processors doesn't hold. And there is yet another architecture called cache-only memory architecture, or COMA as its brain-dead acronym. So we're going to discuss these kind of scalable systems in a little while, but what we concentrate on in this lecture here is how to make the SMPs more scalable. This is a picture showing the good old Snoopy-based cache coherence system. In this picture, the processors are at the top, and then caches below them, and then all the caches are connected with each other, as well as to the memory modules using this Snoopy cache coherence bus. Even though this looks like a thin wire in this picture, we all know that that thin wire symbolizes quite a lot of parallel wires. So we have something like in the order of maybe 300 or so data wires, maybe 50 or so address wires where we send address and command. Then we have other groups of signals with fewer signals, snoop wires, arbitration, data D, and D status. Maybe these signals together is another additional 50 signals or so. So it's a large number, 400 signals, and the good news about this kind of Snoopy coherence is that the system will see a fairly low latency for its coherence activities. So whenever one of these caches wants to perform a coherence activity, it broadcasts it on the bus, and all the other caches will see it right away and can take action right away. Another good property is that, as we also have seen, the fact that we send one transaction at a time across this interconnect, the Snoopy bus, makes implementation of stronger memory models also easier. But the drawback is that this is not a very scalable system. You can't build systems with many caches and or systems that support lots of bandwidth between these caches and memory. And two of the major reasons for that is that each of these wires have lots and lots of devices or caches as well as memories hanging on them. So we have transistors that wants to send and transistors that wants to listen, many of them on the same wire, and that is referred to as the number of loads on the wire. And the more loads you have on the wire, the higher is its capacitance. That's a drawback when it comes to high bandwidth designs. Another drawback comes from the fact that you have long wires. So long wires means that the resistance of the wires goes up, and capacitance and resistance are the two largest enemies of fast signal propagation. So high capacitance and high resistance is a really bad combination here. So that means, and since you have a slow signal propagation, that means that the frequency at which you can drive these kind of buses is going to be fairly low. There are many examples of this, commercial examples, very successful examples. And most recently, Intel had this what's called their front-side bus, which is a Snoopy-based cache coherence protocol, very similar to the kind of protocol that we've been discussing in this course. The front-side bus connected several multi-core chips. This was during the Core 2 era of their design. So how can you make these kind of implementations more scalable? How can we make SMP implementations more scalable? Well, we're going to discuss 5 different tricks you can use to improve the properties of Snoopy or of SMP implementations. One is to, instead of having a single physically shared bus with all these loads on each wire, what we could do is to implement a logic bus. So this could be a logic unit on your chip, for example. We call that, and inside here we use gates that are close to each other to implement these broadcast mechanisms. Each cache is connected to this logic bus with point-to-point wires. So these wires has one sender and one receiver. So we see the address why we double the number of wires here, but just have one receiver and one sender. That means that this is the fastest you can have a wire. Just 2 loads on the wire, and it's point-to-point. So that's good news when it comes to the frequency at which you can drive the signals. So it's a point-to-point interconnect to the bus. That means bad news is it's higher latency, because instead of just putting your message directly on the bus, we now have to send them across this serial link to the bus wire, to the bus logic, and then after the bus logic has decided the point in time at which this transaction is sent, then that the fact that the snoop happened has to be transferred across these wires out to the caches so they can perform their snooping. High latency, but higher bandwidth as well, due to lower resistance and lower capacitance. Still, we're going to have the nice property of the trivial memory ordering, because this bus logic here is going to send the transactions one by one, so there will still be a defined order between those transactions. Second trick we're going to talk about is a hierarchy of these kind of buses. So of course, if you would like to make the wires shorter and reduce the number of wires in the system, having a hierarchy of these buses would get you that kind of property. So here we just have a few of the caches connected point to point to one of these buses, and whenever this bus logic decides that a specific transaction is the one that it would like to promote next, it's going to send that transaction up to the next level, the top bus. And whenever the top bus logic decides that this transaction happens, that's the point in time we're going to put it into the Snoop order. So we're still going to have the same kind of Snoopy kind of property of this, even though there are many point-to-point wires implementing this the network, our broadcast network. Short wires, that's a big plus, but now the latency is even longer, so we have to wait until our transaction, the hero, makes it up to the top bus, and it's declared that it's the winner of that bus. From that point in time, that information has to be synchronously sent down to all the caches, so they can take action and snoop and produce snoop results, and tell if they have the cache line in dirty state, and so on. So we still have all that the snoop mechanism taking place. It's only that we add latency with this hierarchy of logic buses. Still, we have a trivial memory ordering, because it's the order in which transactions happen, and the top logic bus is going to define the order. And there are a couple examples from commercial examples where people have implemented these kind of systems. Another option would be to, instead of just having one bus, let's say in the previous example, instead of just having one top bus, we could decide to have several top buses. And even if it is not a hierarchy of buses, even if you just have one level of buses, we could have several buses. And for simplicity, I just going to talk about 2 buses here, but you can extend it to 4 buses or 8 buses. And what we're going to do is we're going to stripe on some address bit. So we're going to look at a specific address bit for each transaction we would like to send, and that bit is going to tell us whether we should send a transaction on the even bus or on the odd bus. So this means we can send 2 transactions in parallel, so we double the bandwidth doing this. Of course, these buses could be physical buses like I'm showing here, or they could also be the logic buses, and I showed you in the previous example. So this is even more scalable compared with just one bus. And actually, the memory ordering it still could have a nice property if we just add this little fix. We add a convention saying, yes, we can send two transactions at the same time, but if we, by convention, just all of us agree that, for example, the odd transaction happened before the even transaction, then we can actually define one unique order between all those transactions, and we can have the nice property for the memory models. And drawback is, of course, that now each cache has to snoop two different buses, so the interface here between the cache and the buses may be more expensive. There are at least two commercial examples of where these kind of multiple bus snooping systems have been successful. And the fourth way of improving the scalability of an SMP, instead of looking at the Snoopy bus, we're now going to look at how we deliver the data. So as you may remember, in the bus example, most of the wires are used to deliver the data. And actually, broadcasting the data is pretty brain dead, because broadcasting an address transaction is nice because that's what helps us define the memory ordering. But the data is just going to be sent point to point, one sender, one receiver. So why broadcast that using that? You can probably imagine that if we use some other kind of interconnect, we're not going to discuss different interconnect topologies in this course, but you can probably imagine that broadcasting is probably the least effective way of building a point-to-point network. So you can use omega networks, or several multi-stage networks, or switches. It would be much more efficient way of using your transistors and your energy. So we're going to have a separate crossbar that only where you only send the data replies, and of course this is not going to be an ordered network like the broadcast network, but it doesn't matter, because when we would like to get the nice property of stronger memory models, we get that by looking at the order at which we send the address transaction, not the order at which the data replies are sent. So using this, we get higher bandwidth for the data replies, not higher snoop bandwidth, but for the data. Maybe it's even cheaper. You can implement the same data bandwidth using much fewer wires than you would otherwise. So fewer pins, but maybe a slightly longer latency. If this is a multi-stage network, it could take maybe 5 cycles. So latency longer, but the bandwidth is much higher. And there are several examples where this has been implemented as well. Now, going to see what you remember so far from this video. Which of these statements are true? So one or many of these statements are true. So take some time, and afterwards I'll explain which are the correct ones. So the first one, saying that have many bus loads result in increased resistance, that is not true. It's the capacitance that goes up when you have more loads. Point-to-point wires can be made faster than buses. Yes, absolutely. That's why we made this logic buses, for example. An ordered network for data makes it easier to implement sequential consistency. That is not true. It's the ordered network for address transactions, for the request, that makes it easier. Longer wire results in higher resistance. Yes, that is true. And signal propagation speed depends on capacitance and resistance of the wire. That is true as well. Now we're going to look at a commercial example of where snooping has been implemented using some of these techniques. So this is a commercial system from a couple of years back, and back then they decided that they wanted to have a fairly large cache, L2 cache of 8 megabytes. And back then you just couldn't fit that much cache on the same die as the CPU. So this cache is implemented using external SRAMs. Still, the dual snoop tags, so this is a dual snoop tag design, the dual snoop tags actually reside on the same die as the CPU itself. So it's the CPU that's connected to a hierarchy are what's called address repeaters here. So these are like logic buses in each one of these. And we have odd and even planes of these buses to increase. So depending on the address of a transaction, you may choose to use the odd plane or the even plane. So what's going to happen in this system is a specific transaction is sent from a CPU to the lowest level logic bus, and it contains command, address, and some unique ID. But the ID actually encodes the identity of this CPU, which CPU number it is, as well as some unique identifier in its own namespace. Whenever that address repeater feel that it's, that this transaction is it's time for its prime time over all the other transactions that address repeater has received, some kind of arbitration, then it can decide to send that transaction to the next level address repeater. And whenever the arbitration inside that address repeater decides that this is the point in time when officially this transaction happens, then it sends down exactly the same transaction to all the other subsystems. So there are 5 more subsystems like the one we're looking at here. At the same time, this little red wire here shows that we send a signal, not the entire transaction, just a signal saying, remember that transaction you sent to me some time ago? Well, right now is the official time when it happens. Just with a single signal, you can send that to the originating address repeater. At the very same time, that address repeater will send down the very next cycle. It will send down the full command, address, and unique identifier, and that will happen in all the other subsystems as well. So, so here we have a system where all the 24 CPUs will get the snooping transaction arriving at exactly the same time, even though we can't physically point at any snooping kind of bus in this design. So using the snoop results, raising the shared hand and the owned hand and so on, the Snoopy cache coherence protocol is going to decide who's going to reply to this. And the reply is going to be sent across a data network. And of course, the reply will have the data as well as the ID. And once more, the ID consists of the CPU number as well as unique identifier. So the CPU identifier here is going to be used as a routing information to route this data package across this interconnect here. So there's going to be a point-to-point message sent only to the requesting CPU and not broadcasted to all the other CPUs. So finally, what tricks was used in this design to make the design faster? So once more, there could be many correct answers. Take a look, take your time to look at this, and I'll give you the correct answer afterwards. So it's actually all of these. So yes, it uses multiple address buses. So this is sometimes referred to as a fat tree as well. It uses an unordered data network to return the data instead of a broadcast data bus. And it uses a hierarchy of logical address buses. So in this example, 2 levels to implement this kind of coherence. And once more, we are still targeting coherence in an SMP or UMA. Later on, we're going to move on to other kind of even more scalable implementations.